Hi, myself Naveen Kumar Saini. In the course Antenna and Wave Propagation, code KEC603, today we are going to discuss about the sky wave propagation. So what is the sky wave propagation and how it is responsible for traveling the EM waves from the transmitter to the receiver? So this sky wave propagation, it is a radio wave propagation, and the wave which propagates through the atmosphere and reflected back by the ionosphere of the Earth's atmosphere, which is called the sky wave propagation. So it is not the ground wave propagation through which it is into the tropospheric environment, but in the sky wave propagation it will transmit from the transmitter at the Earth station, and it will pass through the different layers, troposphere, stratosphere, and then the ionosphere, which is the last, we can say the last layer for the propagation of the waves. So it will reflect it back by the ionosphere and it will come back to the receiver at the Earth. So these waves from the transmitter and it pass through the sky and it will reflect it back by the ionosphere and it comes to the Earth's atmosphere at the receiver side. So this sky wave, which are practical importance and at the medium and high frequencies for very long distance radio communication, and the frequency range for the sky wave propagation is 2 to 30 megahertz. So this is a range for sky wave propagation from 2 megahertz to 30 megahertz. So these waves, which are transmitted from the transmitter antenna and reflected from the ionosphere, as I just said, it consists of several layers of charged particles, because in the ionosphere is made up of different charged particles, and with here the densities of the charges will be different in the night and in the daytime. So at the temperature changes, so based on that the density of the charges will be changed. So the ranging in altitude, this is from the 32 to 50 miles above the surface of the Earth. So such a wave which travels from the transmitter to the ionosphere and reflected back to the receiver on the Earth also is called the sky wave propagation. So this ionosphere, which is ionized layer around the Earth's atmosphere and which is suitable for the sky wave propagation. So this sky wave propagation is not into the troposphere, it is above the troposphere and then the stratosphere. The last is the ionosphere from which it will be reflected back. So what are different layers? As I said, the first layer is the troposphere, which is very near to the Earth's surface, so which lies just above the ground, and the flora and the fauna lives in this layer. So the ground wave propagation and LOS propagation takes place into this region, which is the troposphere, and then above the troposphere, just like if this is the Earth surface, so this layer is the troposphere, and above that this is the stratosphere. So this is the layer of the Earth which lies above the troposphere, and the birds can fly into this region. So the airplanes which can be travel into this region, and ozone layer is also present in this region. So the ground wave propagation and LOS propagation takes place into the stratosphere as well. Then next is the ionosphere. So this ionosphere, which is the upper layer of the Earth's surface or the Earth's atmosphere, where the ionization is appreciable and the energy radiated by the sun and only hits this region to the ionosphere layer. So this sun will hit this region, and it will produce the positive and negative charges or the ions. Since the sun consistently radiates UV rays and air pressure is low, so this layer encourages the ionosphere or the ionization of the particle. So this ionization occurs by the sun, which will divide these particles into positive and negative ions. So when we talk about the architecture or the structure of the ionosphere, so there are different layers are there into the ionosphere. So just like D layer, E layer, F layer. Okay, so how these layers are divided or it affects into the day and night time. So we will discuss about that. The ionosphere is composed of 3 layers, which is called the D layer, E layer and the F layer. So into this, the lowest layer is the from the lowest layer, which is the D layer, to the highest layer, which is the F layer. Okay, so F layer is further divided into 2 parts. So as we said, the F layer is this division of the layers depends on the time or the temperature, daytime or the night time. So the presence of the or the absence of these layers in the ionosphere and their heights above the earth varies with the position of the sun. So this ionosphere will be this effect into the ionosphere will takes place by the sun. So the D layer ranges from the above 50 to 90 kilometer, and ionization in the D layer is low because it is the lowest region of the ionosphere. So this layer has the ability to refract signals of low frequencies, and these high frequencies pass through it and is attenuated in the daytime as well. So after the sunset, this D layers disappears because the rapid recombination of the ion. So as the sun is there, so due to the presence of sun, it will heat up the charges. So because it heat up the charges, the positive and negative ions occurs, and due to which the different layers of the ionization will be there. So into this, the D layer will be disappear when the sun is not present. So but when the sun is present, in that case D layer will be separated out from the E layer. Otherwise this D layer will be submerged into the E layer as well. So this representation, by this diagram we can represent that how the ionization takes place. So lowest layer is mentioned as the troposphere. Above then we have the stratosphere, as we said, and after that we have the ionization. So this ionization layer is divided into the basically 3 parts: D layer, E layer and the F layer. So when the night is there, in that case this D layer and E layer will be merged with each other. But when the sun is there, when sunlight is there, so due to the ionization of the charges into the ionosphere, in that case D layer will be appeared into the daytime, and this F layer will be divided into the 2 parts, F1 layer and F2 layer. So these are the heights from the earth's surface, which is representing the different heights of the layers, just like the F1 layer. So F1 layer will present from 140 to 250 kilometer, and above that F2 layer will be 250 to 400 kilometer. So it means if in the night time, then combined layer will be the F layer. So in that case the height will be approximately 140 to 400 kilometer. This is the height of the F layer when it is the night time. Otherwise in the daytime F1, F2 layer will be separated out. So here it is also again mentioned this in the flat surface of the earth. Above then we have the D layer, then E layer, then F1 layer and then the F2 layer. So above then that is the G region also. This is the outer region of the ionosphere. So above the 400 kilometer onwards, above this height, the outermost region is called the G region, right? So into which the different other satellite communication kind of applications can be occurred. So these all are the informations about the different layers which we had just discussed. The E layer, which limits about 90 to 130 kilometer, F layer 140 to 400 kilometers, so and so on. So it is representing the how these layers will be created into the ionosphere by the presence of the sun. If it is sunset is there, based on that the different layers will be disappear, just like the D layer will be disappear. So now come to the very important part of this when application of the ionosphere, that is we want to find what is the refractive index of ionosphere, because as we said, the ionosphere is made up of the different layers of the different densities of the charges. So when the wave will propagate from one medium to another medium, so in that case the refractive index will change. Okay, so based on that, what are the parameters which will be responsible for changing the refractive ionosphere region? So for that one we will come to the one derivation which is very easy and very interesting and important as well for the exam point of view. So for that, at any height we are considering the ionosphere. So into which as we are saying that different electrons are there, the electronic charge is present into that, and the mass of the charge is the m. Okay, so in this case we are very much aware about the electrostatic field. What is the electric field of any value of the charge is given by the, because we are very much aware in electrostatic wherever the charge is present, so due to the presence of the charge, electric field will be around that. So in that case the electric field is equal to Em sin omega t. So this is sinusoidal effect of the movement of the charges. So which is acting as a cubic meter of the space in the ionosphere, which is assuming the one given volume into which the charges are present, it is moving with some velocity. So omega is the angular frequency, Em is the maximum amplitude of the movement of charge, and the force exerted by the electric field on each electron is given by F is equal to minus small e into capital E Newton, right? So E is the charge of an electron in the coulombs. So now come to the next part of this. Let us assume that there is no collision. So we are assuming these charges are moving, but there is no collision into that. There is no loss of energy. Then the electron will have an instantaneous velocity v meter per second in the direction opposite to the field. So in this case, the force value will be equal to mass into acceleration, as we are very much aware about this formula, m into a. So force is coming from this equation, that is small e minus e into capital E is equal to m dv upon dt. V is the instantaneous velocity and dv upon dt is the acceleration, that is nothing but the small a. So m into a. So now dv upon dt, we are doing some manipulation to this equation. So when we manipulate this, then in that case dv is equal to minus capital E small e upon m into dt. So when we integrate this equation, so the expression which we are getting, that is v is equal to plus sine small e em cos omega t upon small m into omega, right? So we are just putting the value of e. How we are getting this? Simply we are putting the value of e as the em sin omega t. So we are simply integrating that. Then the instantaneous velocity of the movement of charge is there, small v. Okay. So now next current density due to moving electrons. So next derivation, second part of this derivation is the current density, which we have to take care. So into this, the capital N we are assuming be the number of electrons per cubic meter. Then the instantaneous electronic current density, which is constituted by these capital N electrons moving within the instantaneous velocity v. So what we are saying, this is the formula for when we have the one electron is there, the one electron is moving with instantaneous velocity, which is given as v is equal to this much. Now we are assuming we have the n number of the charges or the electrons are there in a given volume per cubic meter. So in that case, in place of one charge, we have the multiple charges, n charges. So there the density is there. So this density is equal to capital N into E into V. So ampere per meter square. So from this equation, we can put the value of V. So this value is Ne d upon small m upon omega, Em cos omega t. So after solving this, we will get the current density due to the moving electrons, that is Je is equal to minus sine capital N small e square upon m omega Em cos omega t, right? So in this by this equation we see that what is the relation between Je and Em. So it shows that the current density Je lags behind the electric field E by the angle of 90 degree, right? So in this way we can represent that the relation between the Je and the capital E. So what is the relation we can see by this formula. Okay, so third part of this derivation, that is the displacement current density. So into this we are very much aware about from the Maxwell's equations. So we are aware that the current density or the displacement current density, that is JD is equal to d capital D upon dt. So we are very much aware from this formula, if you are very much aware about what is the J plus JD. This is a Maxwell's equation in the time varying field. Into this, this JD is the additional factor which occurred due to the displacement current density, and this displacement current density is responsible for all the wireless communications. Okay, if this value is 0, so in that case there is no wireless communication, it is a static electric field. Okay, so now we are taking this JD as the JD is equal to D capital D upon dt. So in D we are aware that epsilon naught into E, this is the value of the electric flux density, small e into E, and capital E is what? This is the electric field intensity. So in place of E we will put the Em sin omega t, and D is equal to epsilon naught E, and this JD, this value will become small epsilon naught Em omega cos omega t. So the displacement current which leads the applied electric field by 90 degree. So in the previous case, this small this value, sorry, in this case we are aware that the current density was the lag behind by the electric field, but this this displacement current density is the leads the applied electric field by the 90 degree, right? So in this case the total current density, that is equal to the JT, that is equal to JD plus JE. So this is nothing but now it will become the JT. The total displacement current density can be represented as JD plus JE. So we can put this value all together. So in this way JD is equal to from this equation epsilon naught Em omega cos omega t, and this JE is equal to minus sign capital N E square upon m omega Em cos omega t. So after that Em cos omega t epsilon naught minus capital N E square upon m omega square. So we can compare it by the values of from these equations. So in this case if we compare like this equation, so we see this is epsilon naught, this is epsilon naught minus N E square upon m omega naught. So in this case we can see in place of epsilon naught we can say the epsilon, because this is a total current density. So epsilon will become epsilon naught minus N E square upon m omega naught. Okay, so this is representing as the with this analogy, this is the epsilon, right? So in this case epsilon is this much. So we are taking epsilon naught outside, so this value will become the relative permittivity. So the relative dielectric constant or the relative permittivity is given by epsilon upon epsilon naught. So this value is we can take it as the 1 minus capital N E square upon m omega square epsilon naught. So now come to the last part of this derivation, that is the refractive index. So what is the refractive index? This formula we are very much aware. Refractive index N is equal to C upon V. V is the instantaneous velocity and C is the speed of the light. So in this case when we can write it, so C is equal to 1 upon mu naught upon epsilon naught and V is equal to 1 upon mu epsilon. Okay. So in this way when we put in place of mu as the mu naught into mu r, epsilon as the mu naught into epsilon naught into epsilon r. So when we solving this, then refractive index will become mu r upon mu r into epsilon r. So relative permeability and the relative permittivity. So for this case we are assuming that the mu r is equal to 1. This is inhomogeneous system we are assuming. So in this case mu will be equal to epsilon, will be equal to the epsilon r. So when we put all together these values, so in this way the refractive index will become this much. This is nothing but under root of 1 minus capital N E square upon m omega square epsilon naught. Okay, this is very important derivation. Most of the time this is asked in the exam. So this derivation is everyone has to try to solve it, how we can get these values. So okay, so now come to by solving this we are very much aware the mass of the electron, that is 9.1 into 10 to the power minus 31. Value of epsilon naught is 8.854 into 10 to the minus 12. So when you put these values and electronic charge, this value is 1.6 into 10 to the power minus 19 coulomb. So when you put all these values into this, then after solving the refractive index will become N small n is equal to 1 minus 81 n upon f square. So if we know the frequency and the density, so based on that we can find the refractive index of the ionospheric layer. Okay, so this is very important. Again, this again very important formula. Most of the time this is asked into the exam as well. Okay, so up to now, this is the next is the mechanism of the wave propagation. One very few we will discuss about this. To solve the refractive index of an ionospheric layer with some given frequencies, so different frequencies are there which we have to be take care of. Okay, so refraction, this radio wave enters into the ionosphere from the underlying ionized medium. So as the phase velocity in the ionosphere is large, the refractive index is smaller, right? So the ionosphere will behave like a rare medium, and as it consequences at the boundary of the medium, then the incident ray will deviate from the straight line path and will move into the ionosphere in the direction away from the normal drawn at the point of the incidence. So it's showing as we move above the surface of the earth and it is into the ionosphere. So in that case, this is the angular incidence and this is the boundary between the two mediums. So this is the unionized medium, this is the ionized medium. So this is the dense medium and this is the rare medium. This is the rare medium. So in this case, when the wave is propagated from this boundary, so in that case it will deviate away from the surface or from the normal component. So in this case, the refractive index by the Snell's law, this again we are very much aware, sin I upon sin r. I is the angle of incidence in the medium 1 and r is the refractive index, refractive angle which is from the normal. So in this case, sin I upon sin r, and we have just solved that 1 minus 81 n upon f square under root. So this is the formula. So as we are moving away, so density will change or increase, and in that case the refractive index will be reduced. So because of that one, the wave will propagate into that, it will go away from the normal. So at the some incidence, the law of refraction will occur, and it is a 90-degree angle. So here value of r is equal to 90 degree. So it will reflect it back towards the earth surface at the receiving side, right? So based on that, the two frequencies are there which we have to take care. First one is the critical frequency. So this critical frequency occurs when the wave is propagating into different layers of the ionosphere, and at some instant of time when the wave is propagating into the normal incident at the surface or the boundary of the ionosphere and it is reflected back. So that frequency is the critical frequency. So the important point into the critical frequency which we have to take care, for a given time, each ionospheric layer has a maximum frequency, so at which the radio wave can be transmitted vertically. This is very important point. So vertical incidence must be there, okay, and the reflected back to the earth. So this is as we said, there are different layers and every layer has a different frequencies. Every layer has the different frequencies through which the wave will be reflected back. Just like if this is the first layer, suppose the wave is propagating to this and it will pass through this medium, and at this angle at the layer 2 it will reflected back. So in this case, this frequency f2 is what? This is the critical frequency for this particular layer. Suppose it is going above, in that case f3 will be the critical frequency for this layer and f4 will be the critical frequency for this particular region of the ionosphere. So the important point is the angle of incidence must be small I must be equal to 0. So in this case again we can see, for the vertical incidence I is equal to 0. When the I is 0, in this case n is equal to 0. When small n is 0, so what will happen? This n will become the n max, maximum value. So here we can write it as the 1 minus 81n, and this is the f square under root. So when the I is 0, by the definition of the critical frequency, n will become maximum, and f is the one, f is equal to fc. So in this case, when you put all these conditions into this equation, so in this case the formula, when you put n is equal to 0, 1 minus 81 n max upon fc square, and 1 minus 81 n up into maximum value fc square. So the critical frequency formula will become 9 into under root of n max, right? So fc is expressed in the megahertz and n max is in the per cubic meter. So below fc, EM wave will be reflected back to the earth by the ionospheric layer, and this frequency determined by the n and the ionic density. So based on the ionic density, we can find the critical frequency of all the layers. Okay, so based on the different layers, the critical frequencies can be calculated. Similarly, we have the maximum usable frequency. So for this maximum usable frequency, in short we call it as the MUF. So for the given angle of incidence, in the case of the critical frequency, we have the vertical incidence. It means small I was the 0. So for a given angle of incidence, the time of the day, there is a maximum frequency that can be used for the communications between the two given locations. The frequency is known as the maximum usable frequency. So critical frequency is highest frequency that can be reflected back to the earth from the layer of the vertical incidence. Okay, so this is not the highest frequency, then that can be reflected for the earth layer. So the highest frequency that can be reflected by a layer depends on the angle of incidence and the distance between the transmitting and the receiving point. So critical frequency is not the maximum frequency which is at the vertical incidence, but the MUF is the maximum frequency which can be reflected back from the ionospheric layer from the into the ionosphere. So for small derivation is for that one is, so refractive index of formula we are aware, n is equal to sin I upon sin r is equal to 1 minus 81 n max upon f MUF. So in the previous case we were writing the FC. Okay, so there was a condition for that. So for the sky wave return to the earth, the angle of reflection, the ICs must be equal to, or R angular refraction must be equal to 90 degree. So in this case, sin square I, because small I is the angle of incidence, it can be anything, but sin R, this is sin 90 degree. So this value will become the 1. Okay, so now we are solving this by taking the square root both sides. So when we are solving this and we are putting the we know the FC square is equal to 91 n max, we are aware, but by this equation we will come to this point that 1 minus FC upon F max, because if you are taking the n max as here, in that case 81 n max is equal to FC square. So after solving this, we will get the one of the derivation, which is again very important, the relation between the FMUF and the FC. So this is the relation between the maximum usable frequency and the critical frequency. The relation for that one is FMUF is equal to FC sec I, right? So in this case, this is also called the secant law, and which gives the relationship between the maximum usable frequency of the reflected wave signal for an angle of incidence I with the critical frequency for a given value of electron density when the angle of incidence is vertically incidence as the ionospheric layer. I hope you understood this derivation, because these are very important, the relation between the FMUF and the FC. Thank you very much.